In this video, we're going to be talking about how do we determine whether a matrix is diagonalizable or not. So the overarching question that I want to begin with is every square matrix diagonalizable? And the answer to that is no. So no. So I'll put a sad face. Okay, so that's kind of unfortunate that not every square matrix is diagonalizable. So let's talk about the issues that we can run into that might make a matrix not diagonalizable. So the first problem is we could run into a situation where we have no real eigenvalues. So if I look at this matrix and we compute its eigenvalues, so if we look at the determinant of A minus lambda I, so I'm going to put these vertical lines to indicate I'm taking a determinant. So I subtract lambda from the diagonal entries, that gives us negative lambda and negative lambda. The other entries stay the same as 1 and negative 1. Taking this determinant now, so if I multiply the two negative lambdas together, we get lambda squared, and then minus what we get when we multiply the 1 and the negative 1. So that'll cancel out this negative and make this a positive 1. Okay, so that's our characteristic polynomial, but then we have to set that equal to 0. So now I got to take lambda squared plus 1, set it equal to 0, and that gives us lambda will be equal to plus or minus I. So there are two eigenvalues. They're just not real. They're not real numbers. So there are no real eigenvalues. So for our purposes right now, we're only considering matrices where the entries are real. And we're going to limit ourselves to vectors that have real entries as well. If we were to lift that restriction and consider the possibility that we could have complex entried vectors, it would be possible to diagonalize this. So we can diagonalize with complex eigenvectors. But we're only going to look at that in the differential equations part of the course. But we will consider these in differential equations in the later part of the course. So let me just bubble this. So for our purposes right now, because we're limiting ourselves to just real eigenvectors, this matrix right here is not going to be diagonalizable because it would require that we have complex eigenvectors. Okay, so there's another problem that we can run into, and this is the one that we care about more right now. This is the one we're going to see more right now. So let's say I have a matrix like this. So this is a triangular matrix. This is upper triangular. This is triangular. So I can read off the eigenvalues because they're just the diagonal entries. So the only eigenvalue here is 2. So it occurs twice. It has algebraic multiplicity too. Algebraic multiplicity is 2 because that 2 occurs twice. Okay, so let's find the corresponding eigenvectors that go with it. So to do that, I look at A minus lambda I. In this case, it's A minus 2I. And I find the null space of this. So A minus 2I. So if I subtract 2 from these diagonal entries, we get 0, 0. The other numbers stay the same as 1, 0. And now we want to find the null space of this. So we want to find the null space of A minus 2I. Okay, so if I want to find the null space, at this point it's already reduced. Let's go ahead and write down the equation for the first row. That gives us that x2 is going to be equal to 0. x1 is free because there's no pivot in the first column. Okay, so at this point, if I write our vector x as x1, x2, let's see, x1 is free, so we leave that how it is. x2 now we know is 0, so plugging that in, we have 0. And if we factor out the x1, then what I'm left with is 1, 0. Okay, so what I want to do next is I want to introduce some notation to talk about eigenspaces. Okay, so the notation I'm going to introduce is I'm going to let E sub lambda denote the eigenspace for the eigenvalue lambda. So for example, in this problem that we were looking at, E sub 2, because my eigenvalue here was 2, E sub 2, so the eigenspace for the eigenvalue 2, is all the vectors that sort of look like this. So a more concise way to write that is it's the span of the vector 1, 0. In other words, all the multiples of the vector 1, 0. That's what the eigenspace is. But now let's try to form a basis for this eigenspace. So the basis for the eigenspace would just consist of this vector right here. So we would just take that vector, 1, 0, and that would be the only vector that's in our set. Okay. All right, so the issue with this now is that we only have one linearly independent eigenvector, but for a matrix to be diagonalizable, there's got to be n linearly independent eigenvectors. In this case, my matrix is 2 by 2, so we would have needed 2 linearly independent eigenvectors. But we need 2 in this problem, because my matrix is 2 by 2, to get a basis for R2. We need 2 linearly independent vectors to get a basis for R2. So as a result, our matrix is not diagonalizable. It is not, let's scooch this over a little bit, not diagonalizable. So on an intuitive level, the reason why that happened was when we looked at our eigenspace, in this case we only had one eigenvalue, 2. When we looked at its eigenspace, so the eigenspace looked like this, here was the eigenspace, the dimension of it was too small. In this problem, I would have needed this dimension to be 2. I would have needed 2 basis vectors in this eigenspace to have enough to be able to form a basis of eigenvectors. Okay, so I want to now state a theorem that'll tell us in general when a matrix is diagonalizable and when it's not. Okay, so here is the theorem. So it says that if A is an n by n matrix with eigenvalues lambda 1, lambda 2, up until lambda p, then the following chain of inequalities holds. So this says that the dimension of the eigenspace for lambda I, that's what E sub lambda I means. Recall, that's the notation that we just introduced. This is always going to be greater than or equal to 1 on one side. And the reason for that is our eigenspace must have at least one eigenvector in it. In other words, the eigenspace has to be at least one-dimensional. And that's got to be the case because for something to be an eigenvalue in the first place, so for lambda I to be an eigenvalue in the first place, there had to be a non-zero eigenvector that went with it. So that's why the dimension is going to be at least 1. So I notice I'm going to need a little bit more room. Let me scooch this EG a little bit down. So EG, let me give myself a little bit more room. And then the other part of this inequality says, well, the dimension of the eigenspace is always going to be less than or equal to the algebraic multiplicity of that eigenvalue, lambda I. So let's look at an example to get a feel for what this is saying. So if A was a 6 by 6 matrix with characteristic equation, let's say the characteristic equation was lambda minus 2 to the 4th times lambda plus 1 squared equals 0. So notice that these powers sort of match up here because 4 plus 2 is 6, and that corresponds to the 6 that I see here in the fact that my matrix is 6 by 6. So the sum of these algebraic multiplicities is the degree of this polynomial, 6. And it makes sense that my characteristic polynomial should have degree 6 because it's a 6 by 6 matrix. Okay, so what this theorem is saying is, well, now if we were to look at the dimension of each of our eigenspaces. So first off, actually, let me write down what the eigenvalues are. So the eigenvalues are, we got lambda equals 2, and we also have lambda equals -1. Those would be our eigenvalues. So now using the theorem, what that says is, if I look at first the dimension of the eigenspace for the eigenvalue 2. So this for sure has got to be greater than or equal to 1, which means when I try to find a basis of eigenvectors, when I try to find the basis for the eigenspace corresponding to 2, there's going to be at least one element in that basis. But on the flip side, this is going to be less than or equal to the algebraic multiplicity. And what was the algebraic multiplicity for the eigenvalue 2? Well, it was 4. Okay, and similarly, the dimension of the eigenspace for the other eigenvalue, so -1, that's also going to be greater than or equal to 1. So the dimension always has to be greater than or equal to 1 for an eigenspace. And on the other side, it'll be less than or equal to the algebraic multiplicity, but for -1, that algebraic multiplicity is 2. Okay. All right, so the second part of this theorem will tell us, well, what has to be true about the dimension for our matrix to be diagonalizable. So it turns out that our matrix A is diagonalizable if and only if, let me scroll up a little bit, the dimension of each eigenspace equals the algebraic multiplicity of whatever eigenvalue we're talking about. So this has got to be true for every single eigenvalue, lambda I. So as an example, in this example I was just looking at here, if the dimension of E2 had been equal to 4, and the dimension of E-1 had been equal to 2, its algebraic multiplicity, then we have 6 linearly independent eigenvectors. So then we have 6 linearly independent eigenvectors. We'll have the 4 eigenvectors, 4 linearly independent ones from the eigenvalue 2, and we'll have the 2 linearly independent eigenvectors from the eigenvalue -1. So because we have 6 linearly independent eigenvectors, that's a basis of eigenvectors. And when we have a basis of eigenvectors, that's when our matrix is diagonalizable. That's when it is diagonalizable. So in other words, the dimension of each eigenspace, in a sense, has to be like as large as it can be. It's got to be equal to the algebraic multiplicity of that corresponding eigenvalue for my matrix to be diagonalizable. So those dimensions of those eigenspaces need to be equal to those algebraic multiplicities for every single eigenvalue. Okay, so next I want to state a theorem that gives us a simple check for whether a matrix is diagonalizable in a special case. So if A has n distinct eigenvalues, so distinct means that there's no repeats. No repeats. Okay, then A is guaranteed to be diagonalizable. So I'm going to give 2 reasons why this is true. So the first reason is, well, based off of the theorem that I just stated, we know that this chain of inequalities holds. So because there are no repeats, there were no repeated eigenvalues, that means that the algebraic multiplicity of any eigenvalue has to be 1. The only way for the algebraic multiplicity to be more than 1 is if there were repeats, because repeats is how we make the algebraic multiplicity bigger than 1. For example, looking back up here, when we had lambda minus 2 to the 4th, that technically means that the eigenvalue 2 is repeated, and it it occurs 4 times. So it's 2, and then 2, and then 2, and then 2. So the 2 occurs sort of 4 times. Alright, so our algebraic multiplicity of any eigenvalue here has to be 1 because there's no repeats. So what that means is for all I, we know that the dimension of this eigenspace is greater than or equal to 1, but it's also less than or equal to 1. So that only leaves us one possibility, that the dimension of that eigenspace has to be equal to 1. In other words, it has to be equal to the algebraic multiplicity of lambda I, which is 1. So this dimension and this algebraic multiplicity have to be equal, and as a result of this, our matrix is diagonalizable. Diagonalizable. Okay, so let me give one other reason for why this is true. So the other reason invokes a theorem that we saw back in section 5.1 about distinct eigenvalues. So if lambda 1 up until lambda n are distinct eigenvalues with corresponding eigenvectors v1 up until vn, we showed back in section 5.1 that these corresponding eigenvectors, so the corresponding eigenvectors for distinct eigenvalues, that set is linearly independent. So we showed that back in section 5.1. So as a result, when we look at this set of eigenvectors, there are n linearly independent eigenvectors in this set. So because there's n of them, and my matrix was n by n, this is a basis for Rn. So when we have a basis of eigenvectors, that's when our matrix is diagonalizable. In other words, we have enough linearly independent eigenvectors to guarantee our matrix is diagonalizable. So our matrix is diagonalizable. Okay, so what I want to end this video by doing is just sort of recapping the process for how we diagonalize a matrix. Okay, so if we have a matrix A, that's n by n, the first thing that we do if we're trying to diagonalize it is we would find the eigenvalues. So let me call them lambda 1 up until lambda p, and then we find a basis for each eigenspace. So I'm calling the bases b1 is the basis for lambda 1, and then up until bp is the basis for lambda p. Okay, so there's going to be two possibilities now. So the first is if the dimension of some eigenspace E sub lambda I is less than the algebraic multiplicity for some lambda I. So even if this happens for one eigenvalue, then in this case, imagine I'm drawing an arrow. So in this case, this would be not diagonalizable. Not diagonalizable. There's even one eigenvalue whose corresponding eigenspace has a dimension that's less than its algebraic multiplicity. It's not going to be diagonalizable. Because in this scenario, we would have less than n linearly independent eigenvectors. And we need n linearly independent eigenvectors for a matrix to be diagonalizable. Okay, so the other possibility is, well, what if the dimension of every single eigenspace, E sub lambda I, is equal to the algebraic multiplicity? So if this is true for all eigenvalues, for all of the lambda i's. So in this scenario, our matrix is diagonalizable. It's going to be diagonalizable. And if it's diagonalizable, well then we go ahead and diagonalize it. But now we diagonalize it. So to diagonalize it, we form the matrix D, the diagonal matrix. So the diagonal matrix has all of the eigenvalues on the diagonal, on this main diagonal. So all of the eigenvalues would go here, and then I put zeros above the diagonal, zeros below the diagonal. That's what makes it a diagonal matrix. And then the matrix P has all the eigenvectors as the columns. So I'm just going to write down that the columns are eigenvectors. And like we saw before in a previous video, when we set up the matrix D and set up the matrix P, we want to make sure that the columns correspond.